Alright, so this video is about induction, and we're not going to talk about what induction is, but rather we're going to talk about why induction works. So I'm not going to be explaining a lot of the details. I'm going to assume that you know a bit about induction beforehand. So what's the first step of induction? Well, you have to prove the base case of a particular statement, say P, and usually that base case is the number 1 or something. So you have to prove P of 1. You have to prove that this statement works for the value 1. And then that's not the only thing you should do. You should also prove something else. You should also prove that if the statement works for a particular k value, then it should work for k plus 1. And we're forgetting something here. There is a for all quantifier. So for all k values, if it's true for p of k, then it should be true for the next k value afterwards. So these are the two steps of induction. What happens once you're able to prove the first and the second step of induction? Then this somehow leads to the fact that the statement works for all k values. And when we're saying for all k values, this really only applies when the universe of discourse for k is the natural numbers, meaning that the statement only works when k is equal to either 1, 2, 3, and so on and so forth. You can't substitute in k for a decimal like 0.13 and expect the statement to work, because induction doesn't work that way, and we'll try to explain why as the video goes on. So the concept of induction hinges around the fact that this whole thing is true, that there exists a connection between the left side over here and the right side, and we're going to try to explore this connection basically. So let's write this in a better way. Basically, if this is true, then this is true, right? So if we're able to prove these two things, then it will somehow lead to the fact that this guy over here will be true. So how do we write that in terms of logic? So if we can prove that P of 1 is true, and right, we have to prove two things. We have to prove that this guy is true as well. Then that leads to this guy being true, right? We have to prove this. So this is the statement that makes induction work. So let's try to prove it. Otherwise, you're just using induction for granted without understanding what it really is or how it works. So this is the to prove side of things, and over here we're gonna have the what we know side of things. And so we have a statement of the form if something, then something else. So this is simple. We can just move this to the left side, and this is going to greatly simplify things. Furthermore, we have an AND statement as well, so we can just separate this into two different bullet points. And now this is much easier to deal with. Alright, so what's the next step? Well, we have a for all quantifier on the left side. This means we can replace k with any value we want. We have 1 over here, so let's try to replace k with 1. Let's just do that. This will just be 1 plus 1, so that's 2, right? And hey, we have p of 1 at the top. So basically, if this is true, then this is true, but we know that this is true. Therefore, we can say that p of 2 is true. Okay, cool. I don't think we'll be using this anymore, so we'll just erase that. Alright, so we know that p of 2 is true. Well, I guess we can try repeating the same step again. So instead of substituting k for 1, we can do k for 2 this time. So let's substitute k for 2. We get p of 2 leads to p of 3. But we know that p of 2 is true, which means that p of 3 must be true. So we can put P of 3 down there, and basically we can repeat the process over and over and over again. And if we do that, then P of 1 is true, P of 2 is true, P of 3 is true, P of 4 is true, P of 5 is true. We just have to repeat the process again, and the list goes on and on and on and on and on and on. So this is the same thing as saying that it works for P of k, for k is equal to 1, 2, 3, and so on and so forth. And this statement above here will be equivalent to this guy as long as the universe of discourse is equal to the natural numbers. Because over here, we show that it works for all the numbers 1, 2, 3, 4, 5, 6, and so on and so forth. So in order to encapsulate that, this k value over here needs to have the natural numbers as its universe of discourse. Because, well, we only proved that it works for 1, 2, 3, 4, 5, 6, 7, and so on and so forth. So we can't replace it with any other value. So let's say that instead of proving this statement, we are only able to prove this statement instead, k plus 2. So how would that change things? Well, let's try to just repeat the process again. We can replace k with 1. This would mean p of 1 implies p of 1 plus 2 is 3. Then since this is true, then we can conclude that this is also true. So we can put p of 3 here. So now we can replace k with 3, and that would give us 3, then 5 on this side. And since, well, p of 3 is true, we can say that it is true for p of 5, and so on and so forth. So then our universe of discourse would have to change, because this no longer works for the natural numbers. Now it works for the odd numbers only. So we have 3, 5, 7, and so on and so forth. So this will be true as long as our universe of discourse is the odd numbers. But hey, what if we are also able to prove that the statement works for p of 2 individually through some other step or some other method? Then what can we do? Well, we would be able to replace k with 2, and we would get p of 2 leads to p of 4. So this would mean that p of 4 is true. And we can keep going on. We can replace this with 4, and we would get 6 over here. So then we can conclude that p of 6 is true, and we could keep going on and on and on and on and on. Now we know that it works for both even and odd numbers. And, well, that's just the same thing as saying that it works for the natural numbers again. So this could be a trick question. For example, it could be difficult to prove this statement, but it could be much easier to prove this statement. Well, if you just memorize the rules of induction without knowing how everything works, then you would say, this is not induction. Even if I can prove it easily, this is useless to me because this is not part of the steps. And you would just give up. But if you actually took the time to understand the true nature of induction, then you would be able to realize that using this as a resource could still work, and that just requires a few modification. All you need to do actually is to prove that it works for p of 2. So I hope that after all this discussion, induction has made a bit more sense, and you're able to basically just understand that induction is highly modular. And what do I mean by modular? It means that you can replace different parts with something else. Like, say, you can replace this thing over here with this thing, and you would have the capabilities, now that you've understood the inductive process, to identify what else you have to do in order to make induction work if you have this part. So for example, to make induction work, if only this part is available to you, then you would have to prove this thing. So you would be able to identify the necessary pieces to make induction work. It doesn't always have to be the same boring step every time. You can find creative ways to do induction. And so And so I hope that I've shed enough light onto this topic, and now you basically understand and you know what you're doing, and you know if you need to take a different step or a different route, and you won't be lost if you take a different route, as long as you have the truth tables and logic on your side, you'll know what to do next. So that's it for this video. Thanks for watching.